Hello, everyone. It's my pleasure to introduce Joao Costalonga, who is from Federal University of Espirito Santo State. He's from Brazil.
Okay, thanks for the introduction, John. Good afternoon, I guess, from most of you. We're talking about contractible edges and elements in free-connected graphs and matroids. So if you find it fancy, it was a friend of mine that designed a mascot for our university based on our logo. Oh, let's start talking. I believe it's better like this. We'll start introducing some terminology. Our graphs may have loops and parallel edges. Otherwise, you say it's simple. We don't think of edges as pairs of vertices. We think of edges and vertices as separate entities and not necessarily related that can be incident to each other. So a graph is given by a set of vertices, a set of edges, and an incidence relation. We see that a graph is k-connected if removing less than k vertices leaves a connected graph. By connected graph, we mean one where each pair of elements is in a common path. This definition, it differs from the usual because we don't ask for the graph to have at least k plus 1 vertices to be k-connected. So for instance, we have those small graphs here now are free connected. Since removing less than 3 vertices will leave a connected graph. Including the empty graph is connected by vacuity in this definition. And this is not free connected since I can remove 1 vertex here or 0 vertices here and leave a disconnected graph. These more general definitions works well because it makes our results more general. And there are some special applications for these small cases. And we have the idea of edge contraction. So when you join the end vertices of an edge into a single vertex and remove that edge in such a way that there are no other edge linking those vertices, this will become a loop. I can think that both ends of the edge is going to the same place. And if you have something like this, like the edges A and B in blue, they will become parallel edges. And finally, the concept of minor. Say that a graph H is a minor of a graph G if H is obtained from G by edge contractions, this operation, edge deletions, and vertex deletions. And an H minor of a graph G is a minor of G isomorphic to H. We always talk about isomorphic. That's how things work. So H minor doesn't mean H is a minor. It means H is isomorphic to a minor of G. And we write H of this usual inequality sign to say that H is a proper minor of G. It's a minor of G different from G. Isomorphic to a minor of G different from G. We will be focusing on 3 connected graphs. There are some things in the sense for other connectivities, higher than 3, lower than 3 too, but it's kind of trivial. But there are results for connectivities higher than 3, but not. It's a way harder thing. say an edge is contractible if the contraction results in a three-connected graph. And one of the results we'll be extending is this one. Let's say that each three-connected graph has at least half of its number of vertices contractible edges. And this is a sharp bound. This is an answer to a question that how many contractible edges we can get in a graph, a three-connected graph specifically. There's another type of question. How are these contractible edges distributed through the graph? For instance, one answer, there are many different answers for this question. One of the answers is this one, by Thomas and Toft. Each three-connected triangle-free graph has a cycle in which all edges are contractible. Here enters a triangle-free thing that will haunt us through this talk. And one of the goals of my work is unhaunt this thing, deal with the triangle-free problem. And a third type of question is about minors. If G has an edge minor, and those graphs are three-connected simple graphs. And added a simple here because when we talk about minor, this will be relevant. This G has a contractible edge such that H is a minor of G contraction E. We call an edge with this property edge contractible edge. That's a useful tool for proofs by induction when you're dealing with minors. And the answer is yes, provided G has more vertices than H. Of course, if you contract one edge, you will get a graph with one vertex less. Okay, this is obviously necessary to happen. So yeah, we can always find this. Actually, Geoff Whittle proved his name is wrong. It's supposed to be with two T's, not two L's. Proved this for matroids. And that's a corollary for graph. We'll get to matroids in the end of the talk. And we can make a mix of the three questions. If H is isomorphic to a minor of G, how many H contractible edges does G have? And how are those H contractible edges distributed? This is what I will be talking about. One of our results is the following. As you can see, G, this is wrong, it's supposed to be H is G, H is isomorphic to a minor of G, not this, what this is wrong. So if H is isomorphic to a minor of G, swap these ones, are three connected and those graphs are three connected and H is simple and G has more vertices than H and H has at least one vertex, then G has a forest. So we'll talk about distributions too, not only amount. And this forest has at least this number of edges, that is the number of vertices of G minus the number of vertices of H plus 1 by 2. And this is Endo's result, Endo Inamoto and Saito's result. When you consider H to be a graph with a single vertex and no edges. So we'll have exactly this number of contractible edges with the additional, come back. The additional information that they are in a forest. So in addition, those edges from the previous theorem, you can pick them in a forest. But okay, this is not the main result, just a motivation. The main result will require a lot of definitions. And back at the triangle-free thing, each triangle-free three-connected graph with at least 9 vertices has at least the number of vertices plus 5 contractible edges, and this is a sharp result. This result is actually not only for tree connectivity, it's for K connectivity. It's a stronger result, but we have this annoying triangle-free hypothesis. Why annoying triangle-free? One of the uses of contraction is using proofs by induction. And you pick a triangle-free graph, you contract an edge. It may no longer be a triangle-free graph, so there is no much use in this context for contractible edges in triangle-free graphs. But what we can say about edge contractible, the other version, with in which I want to preserve a minor, not only preserve the three connectivity. Then another consequence of the Mann theorem is that, again, I wrote it wrong, Ctrl-C, Ctrl-V, error propagation. If we have H and G, three connected graphs, and G has an H minor, H is simple, and G is triangle-free, then G has a forest with order of G minus order of H contractible edges. And I thought that this number, there is a fancy +5 here. When you go to when you start to requiring the preservation of an H minor, this is sharp. And well, the number roughly doubles when G is triangle-free. This is the cool thing about this theorem. That's not so cool about this one. It's something of an order 1/2 of the difference of the orders. And here we have something in the order of the difference of orders. So the idea now I present a result that capture the information of all these results I presented up to now, but I'll need quite a lot of definitions. So if you don't remember further, you can ask me to remind you. First, we start with the concept of skewness. We see that a family of sets of edges in a graph is skew if it has pairwise disjoint members, and each circuit is the edge set of a cycle, contained in the union of the members of F is contained in a member of F. Let's draw it to make it simple. Let's generalize the idea of forest. The family of singleton sets of edges is skew if and only if its union induces a forest. So the idea of forest that said before would be generalized to the skew families. And here's an example of a skew family. Think of each color class of edges as a member of the family. So we have cycles here, but each cycle, for instance, this triangle is inside a member, inside of this light green member. We have cycles inside of this dark green member, but no mood-colored cycles. So this is skewness, and this is not skew. Skew, not skew. We have now a mood-colored cycle. So this is not a skew family. Next concept, I guess many of you know already about fans. We'll talk about specific type of fan that's a Y to Y. Y is like in delta Y. when we have a degree 3 vertex, think of the circled vertex as degree 3 vertex, a y is the subgraph induced by these 3 edges incident to a degree 3 vertex. So a y to y fan in a graph is a subgraph like the following one. We have a fan that's a subgraph like this, where all these circle vertices have degree 3. And in a fan, you may start with the triangle and end with a triangle, but here we require to start and end with this y's, this degree 3 vertices. And here's an example in a wheel. We may have this last vertex equal to the first one, but nothing else equal to the other, like the edges must be all different, all the other vertices must be different. The only exception that we allow is this first and last vertices. And the example where this happens, the only case this happens is in a wheel for a three-connected graph. And it's like this. So we have a further thing to define about fans is that if we have an H minor of a graph G, we say that a set of edges is an H inner fan if it's a set of edges within a Y to Y fan, within a maximal Y to Y fan, and the contraction of all its edges result in a three-connected graph with an H minor. So we are no longer thinking of contracting edges in order to preserve three connectivity and the minor, but also contract this entire structure. And this is an example in the wheel. If you contract everything, you get a three-connected graph that is a graph with two vertices and a lot of edges between, 3 edges actually between them. It's three-connected by our more general definition. So now we are considering inner fans and contractible edges. Those they are objects we contract. And a family that has as members inner fans and singleton sets containing contractible edges we call a fan family. If we're talking about age inner fans that contraction preserve age, the age minor, and the singleton sets containing age contractible edges whose contraction preserves the age minor and free connectivity. We say that this is an age fan family. So age inner fans or singleton sets with age contractible edges. And instead of sets of contractible edges, we will be talking about these age fan families. And in a moment, you'll see why and how this works. And the last definition, hope you still have some RAM memory to register this all, is the idea of rank. We have a set of edges. The rank of a set of edges is a spanning forest for the graph induced by these edges. For instance, here we think of the set of non-black edges. A spanning forest for these is this one with the red edges. So the rank of the set of the non-black edges has rank 1, 2, 3, 5, 6, 7, 8, 9. So this is how we measure the rank. And finally, this is one of our big theorems, at least the big theorem for graphs. It will become a big theorem for matroids. Sorry, I have some issues with my keyboard that just fell on the ground. Okay, say that we have three connected graphs, G and H, such that H is simple. It has at least one vertex, and G has an H minor. Then G has a skew fan family with ranks of the members summing to the order of G minus the order of H. So we capture this order from that triangle free result. If you think of triangle free, we won't have those fans because those fans have triangles. Thus, this will become the triangle free version. You just add triangle free, that thing that adds a corollary to this. And there is the other result that say that we can pick the edges in the order of a half this difference. I'll talk about it next. And this is the question from where it comes and where it goes first. We'll say where it goes. And this is the theorem I stated before, that with the wrongest statement that I did before, Ctrl+C, Ctrl+V, error propagation. If G has an H minor, not this thing, and G and H are three connected, and H is simple, and G has more vertices than H, and H has at least one vertex, then G has a forest with at least order of G minus. And come from the previous thing. It's the following. Think of a skew fan family. You have some fans, you have some contractible edges that are here in blue. And there's a special kind of fan that is a single triangle with 3 degree, 3 vertices. Well, in this family, we may pick those edges in the following way. In each fan like this, we'll pick these edges. If this is an H inner fan, those edges will be H contractible. It's not very hard to prove. And in this case, we don't have the H contractible edges, but we may do this switch operation. Instead of picking those red edges, we pick, this one. And well, I'm picking something out of my family. This may compromise skewness, no, because every cycle that has these edges must have one of these two. So when I throw out these red edges and pick this blue one, I'm not creating a mood-colored cycle, a cycle that crosses the members of families. So yeah, this preserves skewness, and the resulting thing with only picking edges will be a forest.
Excuse me for a second. That prior picture does seem to have 2 vertices you can remove that disconnect the graph.
Oh, okay. This was not supposed to be the entire graph, only the members of the family. Yeah, I should have draw a light gray thing to be an entire graph. Okay.
Okay. Thank you.
All right. Okay. Okay, this is the theorem I stated, and there is the triangle free version that, okay, already commented how you get one from another. And the other question from Eric comes a bit of idea how this result works. There is an interesting methodology in this work. First, we talk about the simplification of a graph. It's a simple operation when you remove the loops, and each class of parallel edges, you delete all of them except for one. And this is well defined up to isomorphism. And we denote by SIG, the simplification of a graph. There is this property that if you make a simplification, contraction and a simplification, and you make a simplification, a contraction, and a simplification, you end up with the same thing. Well, the first naive attempt to prove this theorem is try to prove something only for age contractible edges. And you pick an age contractible edge and expect that in the contraction, the simplification of the contraction, expect that this edge will behave well in your big graph. This is the strategy that Rito used. And well, this will fail. And Rito described what happens when this fails. You get frustrated, it's not true, but well, some things like this will appear when you have F contractible in the simplification of G contraction E, but not contractible in G. Something like this will appear. And here we have some nice properties that either you have another degree 3 vertex here, or this edge will be contractible. So you cannot pick F, but either a fun will start to appear here, or you can pick this red edge instead of F. This is the first idea when you're trying to prove this theorem. The inner fan appears as an obstruction. Now, here's the different thing in this technique, is when you find an obstruction, you don't stop and say, this not happens because of this. Well, let's try to carry on the obstruction. Incorporate the obstruction to the statement and repeat the procedure. Now we'll just try to raise structures from the simplification of the contraction of E in G may be a bit complicated. Because of, okay, you contract the thing, may appear a lot of parallel edges and lots of triangles originally. You eliminate a lot of stuff. It gets a bit complicated. So we raise the structures from either the contraction or the deletion of an edge that is free-connected and has the same minor. And this exists because of Seymour-Splitter theorem. This is for matroids too, but the corollary for graphs is that if G has an edge, if G has an edge minor and is free-connected, it has an edge E such that the contraction or deletion of E is also free-connected and simple with an edge minor. With the section when G is a wheel. But it's a very well-behaved case, so you can treat it separately. And in the case that you can do it with the deletion, we pick a family satisfying the theorem for G deletion E, and each member of the family will be a union of a skew family, a skew family of inner fans and contractible single edges, with rank summing to R of XY. So actually, it's a skew family of age inner fans and age contractible singletons sets. To be an age fan family, each of the members will have inside of it an age fan family. And okay, you can pick all these guys and put together and assemble your family. It's this thing is not very easy to prove too, but the general strategy is quite simple, straightforward. Then you try to do the same for G contraction E. But we add the contract. This will be a contractible edge, an H contractible edge. And we'll try to add this guy to get the right rank since when we contract to reduce rank. So we need get a thing with a rank slightly higher to satisfy the theorem. And now we get frustrated again because, well, as I said, doesn't work. Contractible edges in G contraction E are not necessarily contractible in G, but the fans will appear. And also the fan, there is this phenomenon where an H contractible fan of G contraction E, which is in red, this figure, imagine this as a subgraph of G, contract E, now you are in G contraction E, and now the Y-to-Y fan is not the entire thing, but it will stop here. And the inner fan will be the set of red edges. But when you look this at G, not at G contraction E, you have a larger H inner fan. So we'll pick the larger fan. What's the problem of picking the larger fan? You add something that was not originally in a set. And now you may compromise skewness. And this is the big difficulty, is to find a skew family until you pick those guys and grow everything. You have to defenestrate some members to keep skewness, but without spoiling the rank. You have to throw some things away because the thing's not skew, but if you throw too much things away, you don't get the desired rank. And okay, inspiration is over, time for transpiration. There's something like 15 pages proof of just deal with the difficulties. There is no clever idea for this. This is done the hard way. Now, there's actually a slightly stronger version. We see that a family is triangle skew if it has pairwise disjoint members, and each triangle containing the union of the members is in one of the members. Now we allow multicolored cycles except for triangles. And this is in a simple graph. And now suppose we have graphs like these. We have G, K, and H, all three connected, and G has a K minor, K has an H minor, and K has a triangle skew fan family whose ranks sum to S. So we suppose the rank may work a bit better for a particular instance K and H. Well, we can carry up with the same technique. We'll have that G has a triangle skew, H fan family with ranks of the members summing to this number, and respectively skew. So if you have two graphs that the thing starts better than the theorems, it keeps get better in the same with the same difference. So the previous theorems, the thing when K equals to H, in this case wouldn't be a proper minor, but it works like this. It supposed to, yeah, it could be equal to here. It also works. And the other thing about the forest, the same technique, you can guarantee that the forest has the forest of contractible edges, now not allowing fans, and it, now it's by 2, but you also have this this difference holding. And okay, those are the results for graphs. Okay, there is the triangle free case, but okay, the things this plus S also preserves in the triangle when G is triangle free. And now we go to the world of matroids. And for those who are familiar with matroids, items A and C hold for binary matroids. We'll be talking about vertical free connectivity. And item B does not hold for matroids, for binary matroids. And for general matroids, A and B failed for general matroids. I conjecture that C holds for general matroids, at least for the simplest case when K equals to H. And well, if you're familiar with matroid theory, now you may have a nap because there will be no news for you. The other work I'll talk about is exactly this. And I believe if you're familiar with matroids, you pick the idea. Now I'll talk, for those who are not familiar with matroids, I'll introduce a bit of matroids. A matroid is a pair where E of M is a finite set and C of M is a family of subsets of E of M such that this is an anti-chain in the order of inclusion. If there is a guy containing the other, they must be equal. This must be non-empty sets, I forgot to say, with following property. If C1 and C2 are different members of this family, and there is an element in the intersection, then there is an element of this family that is the union minus this element in the intersection. So this is a matroid. Okay, one thing more, the members of this family is what we'll call the circuits of the matroids. And this set we call the ground set of a matroid. You must conjecture that this generalizes the concept of circuits in graph, and this is right. But we'll be concerned with binary matroids, and this is what we're talking about. In a binary matroid, we have an additional property that the symmetric difference of circuits is a disjoint union of circuits. So in particular, this property is a consequence of this more particular property of binary matroids. So we may think of only of binary matroids. The finite set, the family of subsets that we call circuits, and the symmetric difference of circuits is this joint union of circuits. And as example, a graph where the ground set is now the set of edges of the graph, and the circuits are the circuits of the graph. You can think if you have a circuit, two circuits in a graph, and you make the symmetric difference, it's not hard to picture that this is a disjoint union of circuits. Well, and there is the dual example. It's a dual in the sense of the dual of plane graphs that you can draw a vertex in each face and cross edges, and you have the dual graph. And the cycles of a graph are corresponding to what we call the bonds of the dual graph. What's a bond? Bond is a minimal edge cut. So now forget about planar graphs. For general graphs, you may have another matroid whose ground set is the same set of edges, but the circuits now are the bonds of the graph. And this is an interesting thing, it's an interesting contribution of matroid theory to graph theory, that you may capture lots of ideas of duality for the non-planar case, and this works wonderfully. But I must say it does not capture all the ideas of duality, of embeddings in surfaces other than the plane, in surface with other genus. The things doesn't work like that. So it's a generalization of the properties of duality for the planar embeddings. And we say that a set that does not contain cycles, we call it an independent set. And a maximal independent set, we call it a basis. It's like in linear algebra. Linear algebra is another example of matroids, vectors, a set in a vector space. And if you pick the linearly independent sets there, it will be the independent sets of a matroid too. But let's talk about graphs. It's where things are better pictured here. And the complements of the basis of a matroid is the set of a basis of another matroid that we call the dual matroid. Write it M star, with the same ground set. And these two examples are in particular duals of each other. I won't say why because I have no time here. And we talked about the rank of a set of edges as the size of a spanning forest for the graph induced by those edges. And here's something similar. Is the rank of a set is the size of the largest independent set within the set. So what's an independent set? Again, is a set that does not contain circuits. In a graph, a forest is something without cycles. So we generalize the same thing. The rank of a matrix is the rank of the entire ground set. It would be, for a generalize the idea of a graph, it would be the number of vertices minus 1. And the idea of scales, it would be very similar to graphs too. Have a family of subsets of a ground set of a matroid. We say that this family is a scale. I'll keep speaking this out. Hard to differentiate one thing from another for Brazilian. We say that this is a scale if it has pairwise disjoint members, and each circuit is containing the union of the members is within one member. And there is the triangle scale case that is the same thing with triangles, not general cycles, general circuits. And now I believe that's the most abstract connectivity in matroids. Case separation in a matroid is a partition of the ground set in a way that the ranks of the members of partition sum is smaller than the rank of the matroid plus k, and each member has at least k elements. This is not exactly the same definition of connectivity for graphs, but it's very similar. A matroid, that matroid associated with the graph is tree-connected if and only if the graph's tree-connected and simple. The difference here that we do not allow small circuits. Like a two-element circuit would be a two-separating set. So a matrix is k-connected and when it has no k separations for k smaller than n. So it's, oh, sorry, it's n connected, it has no case separations for k smaller than n. Okay, this arithmetic criterion is like when you have a graph and a two vertex cut, and imagine there are some edges here and some edges here. Well, we'll have, if you can imagine the spanning forest, they will behave in a way that the sum of the sizes will be one more than the spanning forest of the whole graph. There will be something like a spanning forest here, and for each side, and I have a two vertex cut. If I put the two spanning forests together, well, there will be a cycle, but if I throw one edge out, now I have a spanning forest of the whole graph. So think of pre-connectivity. This is not hard to see how one thing generalizes other if you think this way. So the results, I believe the results, okay, there are more definitions, sorry. We have the idea of deletion, edge deletion, that becomes element deletion in matroids. We simply consider the ground set of the deletion as the ground set without the element you want to delete, and the circuits being the same set of circuits, but we only keep those ones who does not contain the deleted element. It's not the same thing that in graph, when you delete an edge, the circuits of the graph with the edge deleted is the circuits that avoid the edge. And there is the idea of contraction. If the element you are deleting is a loop, this is a singleton circuit, the contraction just the deletion. You may think that contracting a loop in a graph is just deleting it. It's the same thing. And if it's not a loop, the circuits are verified to be the minimal members of C minus E, where C the circuits of the original matroids. You can see this holds for graphs too. One other way to see it's like you look at the dual matroid, delete and take the dual again. It's the same thing. And usually we work a lot with the dual matroid when talking about contractions, because well, this operation is sort of trivial. This is not that trivial, but if you look at the dual, it becomes trivial. And the simplification of a matroid as the simplification of a graph, you remove the loops that are the singleton circuits, and you delete an element of each two-element circuits exhaustively up to the point that there are no two-element circuits left. So it's the same thing when you have parallel edges in a graph and delete one of the two. This is a two-element circuit, and you are eliminating one element of this. We'll be talking about isomorphism of matroids, if you're not familiar. And we say a matroid is isomorphic to the other matroid. There's a bijection between the ground sets that a set is a circuit if and only if the respective image is also a circuit. This defines the isomorphism between matroids. And we have the idea of minor. I would say that a matroid N is a minor of matroid M if N is obtained from M by a sequence of deletions and contractions, and an N minor of M is a minor of M, which is isomorphic to N. And you use the same notation. And finally, the idea of fans. What's a fan in a matroid? Well, in a graph, you have if you recall those two examples of matrices obtained from graphs, one has as circuits the circuit of the graph, and another has the bonds. So this degree 3 vertices in interconnected graphs, they are those edges incident to a same degree 3 vertices is a bond of the graph. So and the bonds are the circuits of the dual matroid. Recalling the dual matroid is that one that has as bases the complements of the bases of the primal matroid. And the bases are the maximal sets, which does not contain circuits. So it's a lot to think of if you want to see it, but we can generalize the idea of fan as a co-circuit, which is a circuit of the dual matroid, and a circuit and another co-circuit and a circuit, a sequence of elements such that each three of them is a co-circuit, circuit, co-circuit, circuit, and so on, and 3 elements each one. So it's a sequence of elements such that each 3 is either a circuit of the matroid or the dual matroid. Beginning with the dual matroid, we're talking about Y-to-Y fans. And finally, what's an inner fan is a fan in which the contraction of all these edges is a set of red edges like this, red elements, if we're talking about matrix, whose contraction of all of them, you can contract one at a time. Doesn't matter the order you contract, you get the same matrix. So it may talk about the contraction of the whole set. This will be a tree-connected matroid with an N minor. And an N-fan family is a family in which members are either N inner fans or singleton sets with elements which contraction results in a tree-connected matroid with an N minor. We call them vertically N contractible elements. There's this vertically because the notion of connectivity of graphs and matrices are slightly different. Vertically is when vertical connectivity is a measure of connectivity in a matrix that really mimics the connectivity of the graph, that example I gave before. We don't use it very much because it's not preserved by duality, and the usual connectivity that are presented is preserved by duality. Now, the general theorem, following, we have 3 matroids, M, K, N, all simple and binary, and N is isomorphic to a minor of K, that's isomorphic to a minor of M. And we suppose that K has a triangle skew N family with ranks of the members summing to S. Then M also has a triangle skew M family, but with the ranks of the members summing to S plus rank of M plus minus rank of K. And moreover, this family is skew, that this is a skew. And this is the main result. If you're not familiar with matroids, it's a lot to process, lots of new information. But let's just, to finish, look at some consequences. Each minimally free-connected binary matrix has a cobasis with all its elements belonging to triads. Won't say what's everything, this is a bit for matrix versed people. Now for the version for graphs, that each minimally free-connected graph with at least 5 vertices has a spanning tree such that each edge not in the spanning tree is incident to a degree 3 vertex. Is a previous theorem by Wu. It said that a triangle-free matroid has a set with its rank plus 1 elements whose contraction of simplification is 3 connected. And this generalized to this, using that result, that a binary matrix with rank at least, not doesn't generalize actually because it's binary. So it's a strong version for more particular thing. With rank at least 4, in which triangle meets at most one triad. You may think of a graph. In a graph, this means a triangle has at most 1 degree 3 vertex. It's more general than minimally 3 connected. It's more general than triangle 3. Then this matrix has a set containing a basis with at least Rn plus 2 elements. And you may think of a set containing a spanning tree with at least the number of vertices plus 1 contractible edges in the graphic case. And there are some strengthenings for the non-regular case. And well, for the graphic case, which is, I was talking about the graphs, this number may be improved to the rank of n plus 4, which is the number of vertices plus 3. So we have the number of vertices plus 3 contractible elements in triangle, in matrix in which each triangle has only 1 degree 3 vertices. Graphs that this happens, not matrix. And so I guess my time is running out. I'll skip this one, go to the last one. One thing about distribution is that each longest cycle of tree-connected graph, non-isomorphic to K4, or the complement of the 6 vertices cycle, has at least 3 contractible edges in the biggest cycle. And this does not hold for matroids, but it holds for binary matroids with 2 different elements, not 3. And I conjecture that the exceptions will be the duals of K3 and 3 dashes. This graph is the K3n when you add a triangle in the 3 vertices class. So if you want to learn more, those are, this is the main work I talked about. There will be a new one that I will put in archive. Soon I'm just correcting some typos. And there is a couple of surveys on contractible edges and graphs if you're interested in the topic. And there's this nice book on matrix theory if you are interested too. And if you want to see something closer to what I talk, it's chapter 12. And well, it's a long read. You can read chapter 12, but if you're interested, this is what I recommend. And thanks for your attention. This is it.
Hey, thanks for your talk. That was a very nice talk. Are there any questions?
Yeah,